Welcome to this slide and this lecture on high-performance liquid chromatography, otherwise known as HPLC. In the previous lecture, we built the theoretical foundation. We looked at partition coefficients, retention factors, plate theory, and the Van Deemter equation. Today, we apply all of that theory to the single most important chromatographic technique in modern analytical chemistry. Every concept from the fundamentals lecture maps directly onto a specific component or decision point in HPLC, and we'll make those connections explicit throughout. Let us begin. There are 7 objectives today, organized around the practical questions a chromatographer asks when developing or running an HPLC method. We start with the instrument itself, then work through separation modes, column selection, mobile phase considerations, and detectors. We finish with the system suitability testing from the USB General. There are 4 worked examples in this lecture, including mobile phase optimization, system suitability calculation, and an HPLC to UHPLC method transfer. I recommend having a calculator available at all times for the worked examples. In today's lecture, we'll follow this roadmap. We begin with a recap of fundamentals and context for why HPLC dominates. Then we walk through the instrument from solvent reservoir to data system, discuss separation modes, elution strategies, mobile phase selection, detectors, and system suitability. 3 new worked examples appear in the mobile phase optimization and practical consideration sections. Watch straight through first, then revisit specific sections as needed. Okay, let's recap lecture 1 from the chromatography section. Before moving forward, let me reconnect with the fundamental section. On the left are the 4 key equations: K for retention, alpha for selectivity, RS for resolution, and the Van Deemter equation. On the right are the key takeaways. Separation equals differential partitioning, optimize selectivity first, and target RS of at least 1.5. In this lecture, every single concept maps onto a specific part of the HPLC instrument. The column chemistry determines alpha, the mobile phase composition determines K. The pump flow rate controls where you sit on the Van Deemter curve. The detector converts separated analytes into a measurable signal. As I describe each component, connect it back to the theory. Why do we use HPLC? Let me motivate you by explaining why. HPLC handles everything that GC cannot. Non-volatile compounds, thermally fragile molecules, large biomolecules, and ionic species. That covers the vast majority of analytes in pharmaceutical QC, food safety, environmental monitoring, and clinical chemistry. More than 60% of all analytical separations worldwide use HPLC. It is the regulatory backbone. Nearly every compendial assay in the USP, nearly every method in ICH guidelines, and nearly every FDA submission relies on HPLC data. Typical analyses take 5 to 30 minutes with nanogram level sensitivity on a UV detector, or picogram level with mass spectroscopy. If you learn one separation technique thoroughly, make it HPLC. Okay. HPLC instrument schematic. So let us look at the flow diagram and component table. The mobile phase starts in solvent reservoirs, typically 2 bottles, one aqueous labeled A and one organic labeled B. The degasser removes dissolved air that would form bubbles in the detector and cause baseline noise. The pump pushes mobile phase through the system at a constant flow under high pressure, somewhere between 400 and 600 bar for conventional HPLC, up to 1500 bar for UHPLC. The auto-sampler injects a precise volume of sample, typically 1 to 100 microliters, into the fluid stream. The column is where separation actually occurs. It's packed with stationary phase particles and usually thermostated for reproducibility. The detector generates a signal proportional to analyte amount. Finally, the data system records the chromatogram and handles integration and reporting. Note the pressure annotation. This high pressure is necessary to push liquid through the tiny particles in the column, and it is what distinguishes HPLC from older gravity-driven liquid chromatography. Something we need to look at closely is the pump. The pump must deliver solvent at constant flow rate under very high pressure with less than 0.1% relative standard deviation in flow. The standard design is a dual reciprocating piston pump. Look at the diagram on the right. Two pistons operate 180 degrees out of phase. While piston A delivers solvent, piston B refills. This gives essentially pulse-free continuous flow. There are two approaches to mixing solvents for gradient dilution. Low-pressure mixing uses a proportioning valve to blend solvents before a single pump. This is called a quaternary pump because it can handle up to 4 solvents. High-pressure mixing uses 2 separate pumps, one per solvent, that converge after the pumps. This is a binary pump. Binary systems are generally more reproducible for gradients, but do cost more. The column is where separation actually takes place. Look at the particle diagrams on the right. The top shows a fully porous particle. Particles all the way through giving high surface area and high sample capacity. The C term in the Van Demeter equation is significant because analytes must diffuse deep into the particle to reach all the stationary phase. The bottom shows a core shell particle, also called superficially porous. It has a solid, non-porous core surrounded by a thin porous shell. Because the diffusion path is much shorter, the C term is dramatically reduced, giving sharper peaks even at higher flow rates. A 2.7 micrometer core shell particle can match the performance of a 1.8 micrometer fully porous particle at much lower pressure. This has been one of the biggest practical advances in HPLC in the last 2 decades. The rule of thumb at the bottom, N approximately equals L over 2 times dP, lets you estimate plates for a well-packed column. Reverse phase HPLC, otherwise known as RP HPLC. Reversed phase HPLC accounts for more than 70% of all HPLC methods. The name reversed phase is historical. In the original normal phase chromatography, the stationary phase was polar and the mobile phase non-polar. RP HPLC reverses this. Look at the diagram on the right. The gray layer at the bottom is the silica support. Bonded to it are C18 hydrocarbon chains, which are non-polar. Above the chains is the polar mobile phase, a mixture of water and organic solvent. The red non-polar analyte labeled NP is buried in the C18 chains. It partitions strongly into the non-polar stationary phase and is heavily retained. The green polar analyte labeled P rides along with the polar mobile phase and elutes quickly. This is the like dissolves like principle. Non-polar analytes are retained, polar analytes pass through. To make a retained compound elute faster, you increase the organic fraction, making the mobile phase less polar and reducing the driving force for partitioning. The most common RP columns are C18 bonded silica, which handles most small molecule analytes in pharmaceutical, environmental, and food analysis. Normal phase and Hillock. So beyond reversed phase, there are 2 other important partition-based nodes. Normal phase uses a polar stationary phase and a non-polar mobile phase. It excels at separating lipids, fat-soluble vitamins, and positional isomerism. However, it has practical limitations. Non-polar solvents do not dissolve polar analytes well, and trace moisture changes retention significant, making reproducibility difficult. Hillock, hydrophilic interaction chromatography, is a modern hybrid. It uses a polar stationary phase with a mostly organic mobile phase plus a small amount of aqueous buffer. The mechanism involves a water-enriched layer on the polar silica surface where analytes can partition into this layer. Hillock is increasingly popular for metabolomics and clinical chemistry because it handles very polar compounds like sugars, amino acids, and nucleotides that simply wash through the reversed phase column. It is also compatible with electrospray mass spectroscopy because the high organic mobile phase promotes efficient ionization. The decision rule at the bottom is practical. RP is the default. Use NP for lipids and isomers. Use Hillock for very polar analytes that do not retain on RP. Isocratic versus gradient dilution. A key decision in method development is whether to use isocratic or gradient dilution. Look at the 2 chromatograms. In isocratic mode on the left, the mobile phase composition is constant. Early peaks are sharp, but later peaks become progressively broader and shorter. This is the general dilution problem. Compounds with high K values spend a long time on the column, and their peaks broaden by diffusion. In gradient mode on the right, you start with a weak mobile phase and gradually increase the organic content. Late diluting compounds encounter progressively stronger mobile phase, which compresses their peaks. All peaks come out with similar widths, improving both resolution and sensitivity for later analytes. The trade-off is that gradient methods require re-equilibration of the column between runs, typically 5 to 10 column volumes of starting conditions. The decision rule is practical. If your analytes span a wide polarity range, K values from 1 to 50 or more, use gradient. If polarity range is narrow, K values from 2 to 8, try isocratic first because it's simpler and faster. Mobile phase considerations. So the mobile phase selection is where you tune retention and selectivity. In RP-HPLC, the two workhorse organic solvents are acetonitrile and methanol. The table shows their key properties. Acetonitrile has a lower UV cutoff at 190 nanometers, meaning you can detect at shorter wavelengths without solvent interference. It also has lower viscosity, which translates to lower back pressure. Methanol is cheaper and provides different selectivity through its hydrogen bonding capability. Critically, switching between acetonitrile and methanol changes the selectivity alpha for many analyte pairs. This is a practical way to improve a separation without changing the column. For ionizable analytes, pH is critical. An ionizable analyte in its neutral form is more retained on C18. In its charged form, it is less retained and often teals. The strategy is to suppress ionization. For acids, use low pH to protonate them. For bases, use high pH to deprotonate them. But note the silica pH limit in the red box. Standard silica-based columns tolerate only pH 2 to 8. Above pH 8, silica dissolves. Hybrid silica columns like BEH technology extend this to pH 1 through pH 12. HPLC detectors. The detector converts separated analytes into a measurable signal. Study the table carefully. UV vis absorption is the default. Robust, sensitive to nanogram levels, and most organic molecules absorb somewhere in the UV. A diode array detector, otherwise known as a DAD, records the complete UV vis spectrum at every time point. This gives both quantitation and spectral identity, and you can check peak purity by examining whether the spectrum changes across a peak. Fluorescence detection reaches picogram sensitivity, but only works for analytes that fluoresce naturally or can be derivatized. Refractive index is universal. It responds to any analyte, but it is not very sensitive and cannot be used with gradient dilution because the changing mobile phase composition changes the refractive index. Ri is standard for sugars and polymers. ELSD evaporates the mobile phase and measures light scattered by the remaining analyte particles. It is universal, works with gradients, but has a nonlinear response. Mass spectrometry gives both extreme sensitivity and structural information. We'll cover LCMS in a later lecture. The distinction between selective and universal detectors is important for your method development. Selective detectors have lower noise and higher signal to noise, but require the analyte to have the right property. So how do I choose a detector? This decision tree guides detector selection. We start at the top. We ask, does the analyte absorb UV or visible light? If yes, we go left and ask whether it also fluoresces. If it fluoresces, choose FLD for maximum sensitivity. If not, choose DAD or UV. This is the most common path and covers the majority of pharmaceutical and environmental analytes. If the analyte has no chromophore, go right and ask whether you need gradient dilution. If no, refractive index works well. If yes, Ri is not an option because of baseline drift. So use ELSD or charged aerosol detection. Finally, regardless of which path you took, if you need structural identification or are working with trace levels, mass spectrometry is the answer. In practice, many modern labs run DAD and MS in parallel to get both quantitation and identification from a single injection. System suitability test. System suitability testing is non-negotiable in regulated laboratories. Before analyzing any sample, you must demonstrate the system is performing within acceptable limits. This table lists the USP for each one. Resolution must be at least 1.5 between the critical pair. Plate count must exceed 2,000. Modern columns typically give 10,000 to 50,000, so this is rarely a limiting factor. And the tailing factor must be 2.0 or less. The retention factor K must exceed 2.0 to confirm adequate retention. And the reproducibility of peak area and retention time across at least 5 replicate injections must have RSD of 1% or less. The tailing factor formula on the right measures peak asymmetry at 5% of the peak height. A perfectly symmetric peak gives TF of 1.0. Values above 2.0 indicate unacceptable tailing that compromises integration accuracy. If any criterion fails, you must troubleshoot before analyzing samples. This might mean replacing the column, refreshing the mobile phase, or checking for leaks. Let's try our worked example. As always, pause and try it first, and then later we will go through it together. Okay, so we're asked to check system suitability. You have two peaks at 8.32 and 8.95 minutes, with base widths of 0.22 and 0.24 minutes, tailing factors of 1.1 and 1.3, and a void marker at 1.05 minutes. We want to calculate K, alpha, RS, and N for peak 2, then check against USP criteria. For K1, 8.32 minus 1.05 divided by 1.05 gives us 6.92. For K2, 8.95 minus 1.05 divided by 1.05 gives us 7.52, which are both well above the minimum of 2.0. This is a pass. For selectivity, we look at 7.52 divided by 6.92, which equals 1.087. For the resolution, 2 times 8.95 minus 8.32 divided by 0.22 plus 0.24 equals 2 times 0.63 divided by 0.46, which gives us 2.74, which is well above the 1.5 requirement. This is also a pass. Let's check for plate count for peak 2. 16 times 8.95 divided by 0.24, all of it squared, equals 22,251, which is, of course, well above the 2,000 criterion. This is also a pass. The tailing factor of 1.3 is also below 2.0, and this is also a pass. All 4 criteria pass. In a real lab, you would also verify that the percent RSD of peak area and retention time from your 5 replicate injections is below 1%. Let's look at our second worked example. As always, pause and try it yourself before we go through. This is a practical method development exercise using the linear solvent strength model. The model says log K equals log Kw minus S times the fraction organic, where log Kw is the retention in pure water and S is the solvent strength parameter. We have 2 analytes with different log Kw and S values. The table below shows predicted K and alpha at various percent organic compositions. At 50%, both K values are too high, 12.6 and 25.1, meaning excessively long run times. At 80%, both are below 2, meaning poor retention. The green highlighted rows at 65 and 70% place both analytes in the K equals 2 to 10 sweet spot. The plot on the right shows the 2 lines crossing through the shaded target zone. Notice that alpha decreases as percent B increases from 2.0 at 50% down to 1.51 at 80%. This is a common trade-off in RP HPLC. Higher organic gives faster elution, but can compress selectivity. For this separation, 65% acetonitrile is the recommended starting point, with fine-tuning from there. This type of scouting experiment, where you systematically vary percent B and track K and alpha, is the standard first step in RP HPLC method development. Let's try our next worked example, the third. So in this one, we're trying to transfer a method that we have in HPLC to UHPLC. Try this out on your own. Method transfer from HPLC to UHPLC is one of the most common tasks in modern analytical labs. The goal is to preserve the same separation on a faster, more efficient system. The key principle is geometric scaling. The flow rate scales as the square of the column diameter ratio, going from 4.6 to 2.1 millimeters. The flow drops from 1.0 to 0.21 millimeters per minute. The injection volume scales by both the diameter ratio squared and the length ratio, dropping from 20 microliters to just 1.7 microliters. The result summary table shows the outcome. Equivalent or better plate count, but completed in about 6 minutes instead of 25, using approximately 1/12 the solvent. This translates directly to cost savings in solvent purchasing and waste disposal. The critical requirement is that you use the same bonded phase chemistry on both columns, same manufacturer, same surface chemistry, so that the selectivity alpha is preserved. If alpha is maintained, the elution order and relative peak positions will be identical, just compressed in time. The RP-HPLC separation mechanism, the molecular view. This molecular level diagram shows that what is actually happening at the surface of a C18 reversed phase column. The bottom gray layer is the silica support. Bonded to it are the C18 hydrocarbon chains drawn as zigzag lines to represent the real alkyl chain length structure. These chains create a nonpolar microenvironment. The mobile phase above contains water molecules, shown as small blue dots, and acetonitrile molecules as orange dots. Now examine the analytes. The nonpolar analyte, labeled NP in red, is buried in the C18 chains. It is hydrophobic and partitions strongly into this nonpolar environment. The dashed arrow shows it slowly releasing back into the mobile phase. The polar analytes, labeled P in green, are riding with the mobile phase. They have no affinity for the nonpolar C18 chains and move rapidly. The ionic analyte, the blue circle with a minus sign, is even more polar and is actively repelled from the hydrophobic surface. The sentence at the bottom captures the essential mechanism. Increasing percent acetonitrile makes the mobile phase less polar, which reduces the energetic penalty for the nonpolar analyte to be in the mobile phase. It spends less time in the C18 layer and elutes faster. That is why increasing percent B decreases K in reversed phase HPLC. Let's look at troubleshooting some HPLC. In this table are some of the most practically useful slides in the series. I recommend saving it for reference. Peak tailing is the most common issue, especially with basic analytes on silica-based columns. It arises from secondary interactions with residual silanol groups. Solutions include end-capped columns, lower pH, or a competing amine additive. Front-loading, peak fronting usually indicates column overload, reduce your injection volume, or concentration. Broad peaks can indicate column degradation. Poorly connected fittings, causing extra column dead volume, or non-optimal flow rate. Ghost peaks come from contamination in the mobile phase, injector, or sample. Drifting baselines suggest temperature fluctuations or column bleed. Pressure spikes mean something is blocking flow, usually a clogged frit or a precipitated buffer. Split peaks indicate a void in the column bed. The prevention advice at the bottom is crucial. Always filter samples through a 0.2 micrometer filter. Always use a guard column to protect the analytical column. Always degas the mobile phase and keep a column log that tracks injections and performance over time. UHPLC, the modern evolution. UHPLC represents the modern evolution of the technique. Sub-2 micrometer particles give dramatically better efficiency per unit. Recall the Van Deemter discussion. Smaller particles reduce both the A term and the C term, lowering the minimum plate height and keeping the curve flat at higher velocities. A 50 millimeter UHPLC column can match a plate count of a 250 millimeter conventional column, but runs 5 to 10 times faster. The trade-offs include the need for specialized high-pressure pumps, more expensive columns, greater sensitivity to extra column dead volume from fittings, and potential friction heating at very high pressures. The block at the bottom highlights an important compromise. Core shell particles at 2.6 to 2.7 micrometers on conventional HPL systems can achieve UHPLC-like performance at conventional pressures. This is because the thin porous shell reduces the C term almost as much as making the particle smaller. For many labs, core shell is in conventional HPLC is the most cost-effective path to better performance. Theory HPLC decision framework. So this slide summarizes the HPLC method development workflow in 6 steps. The first step is to choose the separation rules. Reverse phase is the default for most analytes. Step 2 is choose the column chemistry. C18 is the starting point, but switching to C8 phenol or polar embedded phases changes cell activity. Step 3, choose the mobile phase, acetonitrile or methanol, appropriate pH and buffer. Step 4, decide between isocratic and gradient dilution based on the polarity range of your analytes. Step 5, choose the detector based on your analyte's optical or chemical properties. Step 6, validate the method, including system suitability testing. Each step involves both the theory from the fundamentals lecture and the practical knowledge from the lecture. In practice, steps 1 through 3 often involve iteration. You try a condition, evaluate the chromatogram, and refine. Today's takeaways. There are 7. So HPLC is the dominant separation technique, which is why you need to invest in understanding it deeply. 2, know every component in the instrument path flow and what it does. 3, start the reversed phase Start with reversed phase C18. It handles most analytes. 4. Percent organic controls K and pH controls ionization state. These are your primary mobile phase levers. 5. Use gradient elution when analytes span a whole wide polarity range. Use isocratic when they do not. 6. Match your detector to your analyte's properties. UV for chromophores, fluorescence for fluorophores, RI or LSD for universal detection. MS for structural identification. 7. Always run system suitability before analyzing samples. This is non-negotiable and regulated work. In the next lecture, we switch to gas chromatography. The fundamental principles are identical, but the implementation differs because the mobile phase is gas rather than liquid. I now encourage you to try these practice problems and the next ones in your own time. Solutions will be posted. Thank you.